Welcome to some more homework examples from section 3.3. This is the latter part of the assignment, starting at about number 17 and going till the end. And it's dealing with what we call circuits. And so some of the problems are going to draw out a circuit for you, and in the other ones, they're going to describe a circuit and you're going to draw it. And so I grabbed these straight from the homework, but because I needed to talk to you and write about them, I just copied them here and we'll work through those examples together. So I have 3 examples for you that should help you understand the circuits a little bit better. And so let's take a look at this one. This is number 17. And the directions I put right on the right-hand side. It says write the circuit and simplify the circuit. They should put if possible. They do sometimes not simplify, but most of the ones I saw did simplify. So if we take a look at this guy, I want to make sure that you see the flow of this. So let me make sure I have a good pen. I'm going to do a different color here. So this is, picture this as the input, maybe even of it like something like electricity. And this is the output, like where we want the electricity to go. So maybe this is the electrical outlet and it needs to go through and come to light up a light bulb here for the output. And the question is how can the electricity go from left to right? And what would need to happen? Well, each one of these circuits each one of these letters, I guess, in the circuit is a switch. And so if we're going to have that power go, I'm going to need to have P initially be turned on. And then I'm going to be able to go here. So now that if I let P go down, then I'm also going to need either Q or P to be on. So I'll do it that way. So it wouldn't matter which order you put them in. So I said Q or P. So this one right here is this piece right here. Then it wouldn't matter which one of these is switched. As long as one of them switched, I'll be good. And then to finish it out, I'm also going to need P to be on and come to the output. So that is writing out the circuit. You would see something similar to that in a list of possible answers. And so we need P to work and then either Q or P. So they'll put that choice in parentheses, and then we need P to work. So this last P is this part right here. And again, you'll see another example as time goes on. So the answer that we have for the write the circuit is done. This is our answer for write the circuit. And so now they want us to simplify the circuit. And so as we go to simplify this circuit that we have written, they're going to make use of some equivalent statements that are in the book. I'll see if I can make a copy of this and put it up on Canvas. But this is the equivalent statements used to simplify circuits because they get a little bit complicated. And remember what we had. I don't know if it will let me draw on this. It doesn't look like it. Yeah, apologize. It doesn't look like it will let me draw on this. But what we have right now, oh, there we go, is we have, remember we had a P and Q or R. We had that guy. Let me back up over there. I think I drew your attention to it enough. I'll underline it in blue. So we'll do this. So look what happens. Basically, if you've done any algebra, we're distributing. This is coming in, and we're going to have P and Q. This OR is in the middle here. So they're pretty easy to memorize for the most part. But again, I would recommend having it with you as you do the homework and also having it with you as you do the exam. So I'm going to take a moment to rewrite. Sorry, I'm still in notes. I forgot about that. And I'm going to come back to my 3.3 homework. And we're going to simplify this. So according to that equivalent statement, this should be P and Q or P and P and P. And so that's what we have right there. Now, P and P, that's interesting. P and P would just be P. And so as we come in here, if I go back to the equivalent statements and we look for something like P and P, I think you see it right here. P and P or P is just P. right? And if that was Q and Q or Q, it would be Q, right? So there's nothing special about the variable. So we can simplify this even further and say, well, this is P or Q, and or P and P. Well, interesting. What we really need to happen, this whole thing is going to be true only if this latter part's true, the P's true. So if P is false, let's see how far we could go. If P is false and Q is true, then right here, we're going to have a problem right up front with the Q guy there. So what really makes a difference is this P guy. This all simplifies that in the end, P has to be true. Only if P is true would this initial and this closing one be held. If only Q is true, then we have an issue because it wouldn't be able to even get to this stage or even out to the output. So it all simplifies down to P. So sometimes they're like that, but you can see if P is switched on, we have one big path. That's a very simple circuit. We don't even have to worry about Q. We just turn on P, which is needed for the beginning and end. It would satisfy the middle. Let's look at number 18. Again, we're going to write this circuit. And so as we go to write this circuit, we can see some things here. We can see that if we go along the top layer, we need P and Q to work. Or we could go along the bottom and need not P and Q to work. Well, that's our circuit so far, right? That would be something that we would look for. So that's one of the answers. And now they're going to ask us to simplify that. So how we can simplify that is taking a look at this guy. We would want to see what could we do in order to simplify this guy. So the one thing that I'm noticing is that we have an and Q in both places. So this could be the same as P or not P and Q, using the equivalent statements where the and statement can just be distributed in with the or in the middle. It's actually, is it the same one that we got to use up here? It is, with the or in the middle there, right? But we're using the equivalent statement in reverse. So let me show you those equivalent statements again. And remembering what we had, we basically had this side right here. We had let me underline it. We had the P and not P, or P, not P and Q. So apologize. So we had P and Q or not P and Q, but it's of that form. And so we can take out the and statement right out front, or in this case, I left it behind. But remember what we had. Maybe you don't remember. Let me come back out here and go to exercise 3.3. Remember what we had. We had P or not P. I think that's on here. Let's go look for P or not P. Well, there it is. Sorry about that. Just trying to get back on the pen. But we have P or not P. So P or not P is always true, because either you have one or the other happening. So this is a true statement and Q. Well, a true statement and Q, I don't know if that's here, but a true statement, yeah. A true statement and Q would be Q, right? Q would have to be true in order for that to happen. And so this simplifies down to just be Q as we go to answer that guy. So they're also going to have us, this is one of the last ones, to draw a picture of the circuit. And so here we have this circuit that's being drawn. They want us to simplify the circuit as well. So let's draw the picture first. So we would have some kind of input, and then we would have a choice, right? So the choice that I'm looking at first is this or statement right here. So I could go this way or this way. So the first way would be an opening with not Q being the decision maker. And the second one would be along there would be not R. And that would get me to my output. Then along the bottom would simply be Q. And that would get me to my output. So your circuit would look something like that. It doesn't need to be perfect, but again, you're not drawing these, you're finding the right picture in the homework. So let's take a look at how we can simplify this. So I'm going to rewrite what we had. We had not Q and not R or Q. So you'll get really good at remembering these equivalent statements, especially the ones that require distribution. So we have not Q or Q, and then we had and not R or Q. So this not Q or Q we already know is true. And this is not RVQ. So a true and a statement is just that statement. So now we're down to here, and that's probably, in fact, I know that it is, as simple as it gets, right? We're going to need to have not R or Q. Okay, so let's talk through that. If it's a not R, well, then that closes this top one. And if the Q is false, then it also closes that other top one there. If it's Q, then it closes the bottom one and we're through. So this is the simplified circuit there. That would get us to our end argument if I just happen to say not R or Q as we looked at that, but looking at it from a circuit. So hopefully you can see that. So if the not R is true, we have a path no matter what. Regardless of Q is true or false. If Q is true, then it has the bottom path. If Q is false, then we have the top path because not Q would be true, and both of those would be true. So it seems to work. If not R is false, then Q could be true, right, in that regard, and it would travel along the Q language there. So seems to work out okay. So this is what we're doing. We're drawing out circuits, seeing images of them and writing them, simplifying them as much as possible. Remember that there's a help me solve this if you'd like to use that. And then, reach out with any questions that you might have about these problems as they come up.